Hello, and welcome to the channel. Today's video is on the normal distribution, and is set at a HSC2 standard level. If you're not taking standard 2, but you still need to use the normal distribution to calculate probabilities for your course, then you may still find it useful. We'll be using the concept of standard deviation we discussed in the previous video to help us calculate probabilities using the normal distribution. Here we're going to calculate the standard deviation of these distributions using the standard deviation formula, showing its use as a good estimator for the distance from the mean. So let's label the points. As you can see in this table, we have the value of each point on the left, and on the right we have its squared distance from the mean. Now for simplicity, we've used distributions that are centered around the origin, so the mean is 0. However, remember that this may not always be the case. But here this means that the squared distance from the mean is just the square of the value. Bringing up the formula for the standard deviation, and here we see the mean, denoted by x bar, is 0, as we've already discussed, and the value n, the number of points, is 6. So we take the sum of the squared values, which is 130, and divide that by the number of points, n, which in this case is 6, and then take the square root. This gives us a standard deviation of 4.65, which is consistent with what we see. Now let's do the same for the second distribution. So adding the labels and generating the table. Again, this is the same as before, x values on the left and squared distances from the mean on the right. And as before, the mean is 0, so the value is just the square of the distance. Bringing up the formula for standard deviation once again, we sum the squared distances, which gives us 218, divide this by the number of values, n, which is 6, same as in the previous example, gives us 36.33. Now taking the square root gives 6.03, which I hope makes sense looking at the distribution. Now let's look at the normal distribution. So this is an example of a normal distribution. The normal distribution is defined by two properties: the mean, which tells us where it is centered, and the standard deviation, which tells us how spread out the distribution is. So in this example, the mean is given by the vertical line about which the distribution is symmetric, and the dotted lines are one standard deviation away from the mean. Here we have labeled the point one standard deviation away from the mean as the z-score. This is important as z-scores are how we work with normal distributions with different standard deviations. Now let's add another normal distribution. This one is wider and flatter than the previous distribution. It has the same mean, but a different standard deviation. We can note this as the dotted lines denoting one standard deviation are further apart. However, they still constitute a z-score of 1. This is important. The z-score is different for each normal distribution and depends on the standard deviation. Notice that the second distribution is shorter than the first one. This may be a bit hard to see on the diagram, but it is another important property of the normal distribution. This is the case because the area under the curve of every normal distribution is exactly 1. So if it gets wider or flatter, it must get shorter. This is a very important concept in probability. As we will see, the probability is often represented as the area under a curve. So now we've seen a z-score, what are they and how do we calculate them? This is the formula for a z-score. So if we want to know the z-score of a random variable x that is normally distributed, it is simply the distance from the mean to that variable divided by the standard deviation. Here it is again with slightly different notation, using the Greek letter mu instead of x bar. This is how it should appear on your HSC formula sheet. However, mu and x bar are the same thing. They both mean the average. So the z-score is just the question, how many standard deviations away from the mean is the point in question? Now let's look at another property of the normal distribution. Here I have centered the distribution about 100 with a standard deviation of 15. Here is the proportional area under the curve, so one standard deviation away from the mean in the positive direction is 34.1%. As the distribution is symmetric, this is the same in the negative direction. If you move 2 standard deviations away from the mean, you have to add the additional area. So 34.1% plus 13.6%, and so on and so on. Another way to look at it, and the way that it's written in your HSC formula sheet, is the area under the curve between a z-score of -1 and +1, or between -2 and +2, and so on, which is 68.2%, then 95.4%, then 99.6%. This continues on, but you aren't expected to know past 3 standard deviations from the mean. So now let's connect these ideas of area and proportionality. Imagine that this distribution represents the scores from a test. What this means is that 68.2% of people had a score that was within one standard deviation of the mean. Phrased differently, they had a z-score that was between -1 and +1. But because, as we said earlier, that the area under the whole curve is 1, this means that the area under the curve between z equals -1 and z equals +1 is 0.682, or 68.2% of the total area. So now let's start solving some actual problems. If someone has an IQ of 115 or has scored 115 on an IQ test, what portion of the population has a lower IQ than them? This is why we picked these values for the diagram. IQ is centered around 100 with a standard deviation of 15. Now we can actually solve this problem just by looking at the graph. So finding the proportion of the population with an IQ lower than 115 is the same as finding the area under the curve up to 115. Even though only a very small number of people have an IQ outside of the 3 standard deviation range, we still have to consider them. So really we need to consider all the way down to -infinity. However, luckily this is easy. Because the graph is symmetric, all the area under the curve from 100 back into -infinity is just half, or 50% of the population. And then we know that one standard deviation away from the mean, 15 in this case, represents 34.1% of the population. So that's the answer. 50 plus 34.1 equals 84.1. So someone with an IQ of 115 has an IQ that is higher than 84.1% of the population. Now let's take a look at a slightly more difficult question. What if we ask the same question but with an IQ of 120? The standard deviation is 15, so we can't just read off the graph like last time. So we calculate the z-score. Using the formula from earlier, we get 120, which is the score, minus the mean, which is 100, divided by the standard deviation, which is 15. This gives us 20 over 15, or simplifying, we get 4 over 3, which is just 1.33 recurring. Obviously, this isn't an integer value like we're used to seeing, so what do we do next? Well, the answer is that we have to use a table of values. Because each normal distribution can have a different shape, we use the z-scores to search the table. And because the z-score is a function of the standard deviation and the mean, and the normal distribution depends only upon the standard deviation and the mean, if we write our table of values using the z-score, then one table will work for all normal distributions that we come across. This is why the z-score is important. So here is a z-table. Now this looks a bit intimidating because there are a lot of numbers, but it isn't actually that complicated. This is a positive z-table, so it only lists the positive z-scores. You can see that the first value in the table is for a z-score of 0, which is exactly half of the population, or half of the area under the curve, as we would expect. So now let's find our value of 1.33. The table is broken up into the integer value and the first decimal point along the rows, and then the second decimal point along the columns of the table. So we find the row starting with 1.3, and the column starting with 0.03, and where they meet, that is the value that we want. In this case, it's 0.90824. But let's just take the first 3 decimal places. What this means is that the area under the curve is 0.908, which, multiplying by 100, gives us 90.8%. So an IQ of 120 means that a person scored higher than 90.8% of the population. And that's it for this video. I hope it was helpful, and stay tuned as we'll have some videos up soon where we go through some questions from real past papers and do a full line-by-line worked solution. Thanks for studying with me, and I'll see you in the next one.